is a Senior Research Fellow at the University of Queensland.
Good morning, everyone. Thank you for attending my presentation. Before the start, I would like to thank all the authors, including Niven Tan, Amy Taylor, Sebastian Contino, David Williams, and Chris Gimba contributing to this project. This project is a collaboration between UQ and ERM. So as you are aware that many of the Australian mining sites are moving to closure, and the closure has to meet 3 fundamental criteria. Safe, not killing people and animals. Second, it needs to be stable, which means over time, erosion could be prevented. The number 3 is non-polluting, which means it is able to store and release the water for vegetation growth, and eventually the landform is able to sustain by itself. And all of those factors must be assessed by the soil cover, and these are the criteria that we must meet. Now, coming into the context, this is the site in northern Queensland. The local rainfall is about 400 millimeters per year, and the evapotranspiration potential is about 3 meters. So basically, there is a water deficit. And the tailings is gypsum. So gypsum itself is able to cement, so it doesn't have a tailing dam. But if you look at the footprint, the majority of the site is actually on the slope. So basically, putting the soil cover on the slope is the primary goal for this cover trial, right? We choose a trial site that is the far end of it. Well, this is not one of them. We actually can see quite a few pyramids far away from that. So you can see even the trial itself is large, but if you look at the whole landscape, this is actually a tiny little patch on top of it. Now, look at the cover designs. So the first one is the very typical, have the permeability reducing layer, and then the ISL, which is used the normal shale, which they have abundant of material. And topsoil is to use to accelerate the root growth at the very beginning. The second one is usually a sort of preferred version where the reduced permeability layer is removed because, as said, the gypsum itself is able to cement, and they can effectively reduce the tailing water uptake to the ISL, which is supposed to be the root accommodation location. So the number 3 is a bit more erosion resistant. It has the calcareous material where it's relatively large. I think many of you have been walking along Coronation Drive. Aside of the river, you see the rocky material. Those are the perfect materials to anti-erosion. But the stock is relatively limited. The number 4 material is relatively rigid. So over time, it doesn't break down, but they have to intentionally mine under the ore. So it's not a preferred option, but at least we can try all of them. So have a look at how it's been constructed eventually. So here you've got a size of a person, and this is the size of the material. You can see that the calcareous stands out straight away. It's much larger as compared to the person. So this is the first trial with the sealing layer at the bottom. The second one doesn't have that slice of ceilings. And number 3 is calcareous. Number 4 is sealed stone. You know, this is like a birthday cake, isn't it? That's what I look at it. So it was quite, it looks quite amazing. And installation was done and backfill. You can see the color contrast is slightly different. This is mostly associated with moisture content because once it's disturbed, there's a little bit contrast between the two. Now, talking about sensor installation, so it was done by excavation, use a 15-ton excavator. So excavated to a depth of 3 meters, putting the sensor in. One of the key things is to ensure that the bottom of the line is lower than the sensor location so that when there is any preferential pathway, this is where the water is going to go, not on the sensors. And then we repeat the whole processes until the whole pit is backfilled with the original material. So that's the overall processes. Next one up is some of the on-site situation. If the pit is relatively deep, we wouldn't be able to walk into the pit. Instead, we actually use a stick to push it and then backfill with the material. So I look at the horizons, so you can see tailings, ISL, and then the topsoil, and backfill with the material. So there's a lot of cable to manage. So yeah. Now, finish all of the setup. We got the weather station. one vertical profile at the downstream, one profile at the upstream, and they all monitor the moisture, suction, and oxygen levels at different locations. So hopefully more water will be accumulated at the downstream side of the slope, a little bit less at the upstream, due to potentially a phreatic surface developed in there. Now, I want everyone to vote. I put all of the information here. So how deep can storm water infiltrate to the covers or tailings? Now, the information listed is number one, the rainfall is about 400 millimeters per year. The second is that the rainfall typically occurs 4 to 6 storms per year. So it's 4 big lots or 6 big lots instead of drizzling every, like all day. Thickness is about 1.6 meters. And the battle slope is 1 to 3 gradients, so it's on the slope. So does anyone believe that the infiltration could go towards the tailings? So 1.6 meters below ground. Anyone believe so? Could raise up your hand, please? There's just 2, 3. How many of you believe that the infiltration thickness is about, say, half a meter? I would say about 10%, right? There are many people who hasn't voted for, so probably much deeper than that, say 3 meters? No one? And most of you believe that majority of them goes by runoff, is that the case? How many of you believe that the infiltration is very, very small and most of them goes to runoff? I would say that's about 20%. Okay, I think we have those survey in the mind. Okay, you have your own bet. Let's look at the result. I tell you my bet. The reason why it's been designed by 1.6 is because we believe that the ISL is able to stop up to that level, right? We don't, if it's just half a meter, we don't have to design to that depth. But the reality actually tells a very interesting story. So look at the rainfall. So this is from June to March. We have longer data, but this one would be very useful to look at the differences. We've got a big storm in the winter, and then a lot of small storms in the rainy seasons. So the topsoil across all of those plots clearly responded to the rainfall, clearly, right? Which is a good thing. But then if you look at the moisture at 0.6 meters below ground level, there is only the calcareous, the large rocky material that allows infiltration to take place. But the rest of them doesn't really pick up the infiltration at all. Okay, what happens then is that we are basically scratch our heads and say, what's going on? Are we install the sensor properly? But I don't think so. We push the sensor quite well. You know, it's well attached to the soil, and it should be able to have a good contact. And the result is pretty consistent. The way how we're able to find what's going on is actually using the on-site footage. So here is the picture that shows immediately before the storm. So you got the vegetation, and you can see the color is relatively dark, so that means the storm is coming. This is the picture that shows immediately after the rainfall. You can see there's a lot of splash. The topsoil get well mixed with the water, and that could potentially fill all of the large pores formed within the ISL, which effectively reduce the infiltration and the permeability of the topsoil. And as a result of that, the infiltration is actually limited. Now, most of the water is stored within the surface, and you've got a slope. What will happen? Surface runoff, right? So you can see that gully started to form, and majority of the water goes by surface runoff instead of infiltrations. So this is the situation after the storm. So you can see quite a bit of gully started to form, and those ones could be deepened over time, right? Now, we've monitored the moisture content, but it doesn't really tell us the water balance, right? The best way to find out the way, you can install lysimeter, you have multiple lines of evidence, but it will always be good to have a numerical model to support the mass balance. So what we did is to use hydrous to simulate the moisture profile over 700 days, so basically 2 years. The lines, the dots here are basically upstream and upper slope and lower slope moisture content measured. The lines here are the simulation results. So you can see that in general, the models capture reasonably well about the rise and falls of the moisture content. Okay, we gain confidence. The model is calibrated. Now, it's a crystal ball. We're gonna do some predictions and see what really is happening. So if you look at the moisture content with depth over time, so 700 days, so the color here shows if it's blue, that means it's high moisture content. If it's red, that means it's dry. So you can see that the moisture content responded reasonably well with rainfall, right? But if you look at the infiltration thickness, it doesn't go beyond 0.5 meter. That's what the model tells, pretty consistent with the observation. Then what we can do, water balance. So this is the cumulative water balance here. So the blue line is the cumulative rainfall. So over 2 years is about 800 millimeters. Now they're gonna slide the cake. So the surface runoff, as shown by the orange color, is about a third of it. So a third of them goes to the surface runoff, and 2/3 goes to infiltration. But infiltration doesn't mean it's net percolation, because you still have evapotranspiration to uptake the water up. So you've got transpiration and evaporation adding up together. It's actually more than the total infiltration into the soil, which means that overall we are losing water. So you see we have a lot of blue, but later on becomes yellow and red, which is an indication that overall we're losing water. So the system has not yet reached a steady state. We still have to keep monitoring. And bear in mind, 400 is actually in the La Nina season. And we're about to reach to the El Nino seasons where the rainfall would be limited. So this assessment is incomplete, right? Now, move on to the vegetation. So thankfully, the video footage, we will be able to see the growth and some of the weeds that do the tumbling and the moving around. And then during the dry season, start off getting yellow. And then during the wet season, it becomes green again. So this is very consistent to another locations where you can see not only the vegetation growth, but also the gully formations. The way how we use it is that we basically choose all of the green pixels and then stitch them together to see the kind of green indexes. And this index is relatively short period. The way to extrapolate it is to compare that with the satellite image, which is shown in the next picture. So this is where the trial is located. So we basically associate these two. If they are agreed reasonably well, from then onwards, we don't use camera anymore. We basically use the satellite image to predict how the vegetation grows over time. This is an ongoing process, so we don't have a conclusion yet. This is 2 years after, so the nature somehow disturbed the mud cake, unfortunately. But one of the takeaway message, as you can see, is that the rocky material, you don't really see a lot of gully to form. This is actually the perfect material to be covered on the surface. So we more or less figure out, probably you don't need a lot of material to cover on the slope, but you do need the rocky materials. So takeaway message, we haven't yet reached a steady state. Infiltration is only the top 0.6 meters, almost no upward flow from tailings to the ISL. And moisture content is decreasing over time, and there is a bit of mixture between the two materials that could effectively limit the infiltration. Number 3 is vegetation is very much associated with the rainfall patterns. And the cover effectively limit the infiltrations. And the last one is that we still have the continued monitoring to understand the vegetation growth pattern. That's the end of my presentation. Thank you very much.